grade 12 learners. Welcome to the Physical Sciences Paper 1 revision lesson. My name is Dimpo Rampora, and this lesson is brought to you by the Northern Cape Department of Education in collaboration with Pakama Research and Development. So in today's lesson, we are going to be looking at paper 1 revision. Hopefully we will cover most of the things that you've already done, but we are not going to do everything, right? Now to start, let us look at the framework. Like, what is it that you must expect when you're looking at the paper, right? Remember that you are going to be given 10 multiple choice questions, which will be equivalent to 20 marks. And then you'll have a structured questions that will be about 130 marks. And this paper will be written for 3 hours, and the total will be 150 marks. Very important to know that. Another thing that I want you to remember is the topics, actually the knowledge areas that are going to be assessed in paper 1, and where are you going to have more marks and which topics to focus on more. So as you can see here, mechanics, it has 65 marks, which has the highest marks so far. We have waves, sound and light, which is 15 marks. We have electricity and magnetism, which is also 55 marks. And then we also have matter and material, which is only 15 marks. You can see that a lot of the marks are lying there in mechanics as well as electricity and magnetism. That is where you need to make sure that you work extra hard in those knowledge areas. Now let's quickly move on to the structure of the question paper. Now remember, this is taken from previous question papers, right? In the previous question papers that we have seen that question 1 is normally your multiple choice question, and it consists mostly of all the topics that will be covered in the paper. And then question 2 is normally your Newton laws, all of them, Newton 1, Newton 2, Newton 3, as well as the universal law of gravitational acceleration. We also have question 3, which is your vertical projectile motion. We have momentum, work, energy and power, Doppler effect, electrostatics, electric circuits, electrodynamics, as well as the last one, which is photoelectric effect. So very important to know which topics and how many marks each topics will have. Okay, without wasting any more time, I want us to first look at question 1 of many previous question papers. We know that the structure of the question paper, it is our multiple choice question. Now I'm going to give you tips on how to answer multiple choice questions. So number 1, I want you to read the question carefully with understanding. Take your time as you read it. And then as you do that, make sure that you can eliminate the wrong answers that you see at first glance. Okay, make sure that you eliminate them, and then it's going to make it easy for you to look for the keywords. Make sure that as you go through the multiple choice question, you look at the keywords. Okay, and then step 4, make sure that you use your logic and reasoning to choose the correct answer. And then also, what is most important, please make sure that you practice time management. Do not spend too much time on a multiple choice question where you still have a lot of questions to answer, especially if you are not sure of that particular question. Very important to look at, check your SI units, check your conversions. They're going to guide you as to which one is the correct answer. When you are done, you then need to sit down and review your answers according to whatever that you have chosen on the multiple choice question. And then the next one that I want to talk to is, please make sure that you practice previous question papers and only look at the multiple choice question, because I know most of us, when we practice, we only look at calculations and the structured questions. We don't practice the multiple choice questions. So please make sure you do practice multiple choice questions. And lastly, very much important, never leave the multiple choice question unanswered. You will rather guess the answer, and then never leave it unattended. Right, let's quickly move on to question 2. Question 2, we indicated that is your Newton laws. These are the following definitions that you need to familiarize yourself with. The examiner can ask you any of the definitions, so you must make sure that you know all of them actually. Now remember Newton's first law, you also need to know how to define Newton's first law. Newton's first law, we know that it states that an object will remain in the state of rest or continue moving at constant velocity unless acted upon by an unbalanced force. force. And if we look at the formula, we know that this is associated with F net is equals to 0. So anywhere we see F net is equals to 0, we know that we are dealing with Newton's first law. Now, the other definition that you need to familiarize yourself with is Newton's second law. Newton's second law, we know that when a net force is applied on an object, the object will accelerate in the direction of the net force, while acceleration is directly proportional to the net force and inversely proportional to the mass of the object. And we know that the formula that is associated with Newton's second law is F net is equals to ma. So very much important to know the difference between F net is equals to 0 as well as F net is equals to ma. And then Newton's third law, we know also how to define that one. I'm not going to do all the definitions because then we won't finish on time. But in Newton's third law, what you need to remember is that the force of action is equals to the force of the reaction in opposite direction. Plus, please make sure that as you define your definitions, they are according to the exam guideline. And which exam guideline are you using in physical sciences? You are using the 2021 exam guideline. Remember here, what you must remember is the force of action. Okay, force of I will be equals to the force of reaction in the opposite what direction. So meaning that the forces will be equal in magnitude but opposite in what? In direction. The universal law of gravitational acceleration, please make sure that you are able to define it, and then the formula associated with that one, remember it is F G, which is our constant, gravitational constant value. You find it in the data sheet. It's going to be provided for you. And then M1, M2 over R squared. Please make sure that this formula, you do not confuse this definition with electrostatics. I mean, actually, Coulomb's law. Please do not confuse the definition of the universal law of gravitational acceleration with Coulomb's law. The next definition that you must know is the friction force. Remember, there are two types of friction, the static friction force and the kinetic friction force. Remember, static is when the object is stationary, and then kinetic is when the object is in motion. Please make sure you need to know all the three definitions. They are not the same, all right, according to the exam guideline. Then you also need to know how to define the normal force, acceleration, as well as inertia. Very much important to know all those definitions. The examiner can ask any of those. The next exam tip that I want to give you in question 2 is to look at how to draw the correct free body diagrams as well as force diagrams. Very much important. It has a lot of marks. It can vary from 4 to 5 marks. Sometimes it can give you 3 marks, but you know, if you know how to draw your free body diagrams, then you know that you at least you have 4 to 5 marks in your pocket. So on your far right, on the right hand side, this one is your force diagram, and over here this one is your free body diagram. All right, you can see that the difference is just the way in which you draw the following structures, the diagrams I meant. Now the first one, which is the force diagram, you can see that the forces here are actually in the exact position of where they are supposed to be according to their own definition. For example, we know that the normal force, it is the force that the surface exerts on the object, and it always acts perpendicular to the surface. Hence, you can see from the force diagram, the normal force starts exactly from the surface because it is the force that is exerted by the surface on the object. However, when you look at the free body diagram here, remember that the object will be represented by a dot, and then all the arrows must be moving away from the dot. As you can see in the free body diagram, we don't really show the exact position of the force. Now remember the two types of diagrams, very much important. And for you to be able to write the correct free body diagram or force diagrams, you need to know the different types of forces. Remember, you have the normal force, which is the force exerted by the surface on the object, always acts perpendicular to the surface. We have weight, or Fg, that force is always acting downwards. I always call it the God-given force because it's always going to be there, all right? So it's Fg always going downwards, and then you have your friction force, your two types of friction, Fk, which is your kinetic friction force, and then Fs, which is your static friction force, all right? And then the other one is Fa or F, which is the force applied, all right? Whether it's the pulling force or pushing force. And then the last one I forgot to mention is T for tension. Remember, you also need to know that there can be a tension force. When do you know that there is tension? Whenever you see a string, a rope, a cable, that is when you know that there is tension force that is there. Right, let's quickly move on to what is it that you need to practice when we look at free body diagrams. Which scenarios according to the exam guideline? According to our exam guideline, it tells us directly that when we do calculations as well as free body diagrams, we need to look at objects that are moving on a flat horizontal plane. Over here, I gave you two examples. Here you have to object A as well as object B. You can see that they are both moving on a flat horizontal plane, and you need to practice those where there is friction or where there is no friction. Practice calculations and practice drawing free body diagrams. Now let's quickly look at object P. I'm just gonna draw a free body diagram for you looking at object P. As you can see, object P is going to be represented by a dot. Which forces are there? I always advise my learners that always start with the God-given force, which is the force of gravity or weight. So that is my Fg for force of gravity or weight. And then also the second thing is that you look at the force that you are already given. Over here, I'm given a string and it's going to the right hand side. That is what I'm going to draw here. I know whenever there is a string, there is a tension force that will go to the right hand side. Now, what else do I see? I see that the object is lying on top of a surface. I know every time when there is a surface, there is a normal force. When there is no surface, there is no normal force. So there is my normal force. Make sure that it is perpendicular to the surface. There is my normal force going upwards because it is the force that is exerted by the surface on the object and it acts perpendicular to the surface, right? Very much important. If you were drawing this object P without friction, that is how the free body diagram would look like. But if there was friction and the motion of the object was going to the right hand side, then our friction force was going to go to the left hand side, because remember, friction force is the force that opposes the motion of the object and it always acts parallel to the surface. So very much important. I would put FK there because I'm assuming that the object is what is in motion. If the object is not in motion, remember that you are going to put the FS for static friction force. All right. The next thing that I want to emphasize here is when we look at object B, is that you can see that we have another tension, but our tension here is acting at an angle of 14 degrees. How do I draw a free body diagram for this one? Remember, you do not include the components. Please, when you draw free body diagrams, you only draw the forces that exist. Even if it's acting at an angle, you draw the force at that angle. You do not include the components. Only include the components when you are doing your calculations. So let's quickly draw the free body diagram for this one. We start with the God-given force, which is Fg going downwards. Then what else do we have? We have T, which is that tension that is acting at an angle of 14 degrees. Then what else do we have? We have the normal force that is always going to act perpendicular to the surface. And then if there's no friction, that is how the free body diagram would look like. But if there is friction, remember that it will oppose the motion of the object. Please do not include the components. Let us refrain from putting Tx and the Ty on the free body diagram, please. All right, let's quickly move on. What is it that the examiner might also give you? According to the exam guideline, you must also practice objects that are moving on an inclined plane, right? Very much important, right? As you can see on my left hand side, I have a diagram here where the object is sliding downwards. When the object is sliding downwards, when they say draw a free body diagram, please, again, if Fg is acting at an angle, do not include the components of Fg when you are drawing a free body diagram. Just include Fg going downwards. All right, Fg must always go downwards. Do not include the components. Only include them separately when you are doing your calculations. And then over here, I'm going to have my normal force. But remember that your normal force must always act perpendicular to the surface. And if the object is sliding downwards, we know that my Fk will be going upwards. All right, very much important to remember that. Let's quickly move on to the next one. Sometimes you will be given objects that are moving at a vertical plane. It can be a lift or a rocket, or the example that I'm giving you here. These ones are very much easy to draw the free body diagram. However, you can see something here. You see that I'm given 2 blocks, all right? Remember, when you are given 2 or more blocks, you must always draw the free body diagram individually or separately for each and every block. It will make it easier for you, all right? Now, let's move on to the next one. Sometimes the examiner, as I said, they will give you more than 1 blocks. These are examples of more than 1 blocks. So as you can see, you must go draw the free body diagram for P, draw the free diagram for Q, draw the free body diagram for 1 kg, for 2 kg separately. Let's draw for 2 kg. You know that you're going to have tension going upwards, and then we have the God-given, which is Fg, going downwards. That is how you draw the free body diagram for the 2 kg block. And then you can draw the 1 kg separately, and also with the 6 kg and the 3 kg together with these ones. Okay, all the different scenarios according to the exam guideline. Go practice them. You will see that the moment you come across the same thing in the exam, you would already know how to deal with it. Now, let us look at which equations must I familiarize myself with when I'm looking at question 2. Remember, question 2 is forces, is Newton laws, which formulas according to the data sheet. You go to the data sheet, you will see a place written force. So under force, I know that F net is equals to MA. I'm going to use that one when I'm doing Newton second law. All right, even when I'm doing Newton first law, but I'll remember that when I'm doing Newton first law, my acceleration will be 0, which will eventually result into F net is equals to 0. Now, this is the formula to calculate the static friction force, but at its maximum. All right, and then this formula is for calculating the kinetic friction force. I might be able also to use it. And then this formula of weight also, I can use it when I'm doing my calculations. This formula over here, remember, I use it for universal law of gravitational acceleration. I can use any of it, and these ones also under universal law of gravitational acceleration. So it's very much important to familiarize yourself the data sheet for each topic, so that you know that when the examiner says calculate the force of gravity, you know which formula to use. All right, this will be given to you. You don't have to memorize them. Now that we are done with question 2, we are quickly going to jump to question 3, which is normally from previous question papers, vertical projectile motion. Now in this chapter, it is a bit challenging to some of us, but where can we get our marks? We can get our marks in definitions. Why? Because there are only 2 definitions to memorize under vertical projectile motion, which is free fall as well as projectile. Remember, free fall is the type of motion at which the only significant force that is acting on the object is the force of gravity, right? And then projectile is the object that is given the initial velocity, and it's also the only force that is acting there is the force of gravity only. Very much important to go and look at those definitions, and they must be exactly according to our exam guideline, right? Only the 2 definitions that you need to remember. Another thing that the examiner can give you also, free body diagrams, they overlap also to vertical projectile motion, but what you need to be careful of is that, remember, in vertical projectile motion, there is only one significant force that is acting on the object, which is weight. So all the time, if they say to you, draw the free body diagram under vertical projectile motion, that is how you are going to draw your free body diagram. It's weight. Why weight? Because we are looking at the only significant force that is acting on the object. It is the force of gravity, right? Now remember, the force of gravity, it is our main guy in vertical projectile motion, and it's very much important to know the direction and the magnitude of weight, right? Remember, the magnitude is 9.8 meters per second squared. Remember, that is supposed to be squared over here. Remember, the moment you say 9.8 meters per second, you're no longer going to be talking about acceleration, but you are talking about velocity. So very much important to take note of the SI units there. So your gravitational acceleration. When we talk acceleration in VPM, we talk about acceleration due to gravity, which is constant, 9.8 meters per second squared downwards. So it's always going to go downwards. Whether the object is going up, gravitational acceleration will always be going downwards. All right. Then the next thing, you need to be able to use equations of motions to determine the position, the velocity, as well as the displacement of a projectile at any given time. Now, very much important to remember when you are dealing with vertical projectile motion is that position versus time graph or displacement. We know that position is displacement. So position and displacement, they are vector quantities. They must have magnitude and direction. Velocity is a vector quantity, magnitude and direction. And then over here, displacement, I've already said, is a vector quantity. It must have magnitude and what? And direction. And then time, remember, it is a scalar quantity. It does not have what? Direction. Very much important to do that. Now, as you practice your vertical projectile motion, I always say to the learners, please do not memorize the formulas. There are so many of them. As you can see, you just go to the part in the data sheet where it's written motion, and then you can see all of these are equations of what? Of motion, right? So you don't have to memorize all these formulas. They will be given to you. You just have to copy the formula as it appears on the data sheet and paste it on your answer sheet. Please do not try to solve the formula before you do your substitution. Just copy and then substitute. Then after substituting, that is when you can try to manipulate the formula. Very much important to do that. We've spoken about all these variables. We know what they mean. We know that acceleration is acceleration due to gravity, which is that 9.8 meters per second squared, right? Now, the other thing that I want to give you is the problem solving tips. What is it that you need to do as you go through practicing previous question papers when it comes to calculations under vertical projectile motion? One, you need to be very consistent with the direction that you are choosing. If you are choosing downwards as positive, please make sure that you become consistent throughout the question. You're going to use downwards as positive, meaning any variable that will be going downwards will be positive. All right, very much important. Or if you have chosen vice versa, where you have taken downwards as negative, also be consistent throughout the entire question as downwards being negative. All right, I've already spoken about that. Then the next thing that I want you to do, when you are being consistent with your direction, you choose your direction, you write that you have chosen downwards as positive. All right. The next thing that I want you to do is to write the list of the known values that you are given in the statement. Then you determine which equation that needs to be used to find out the unknown value. However, as you are collecting the list of the known values, wherever the value consists of a vector or that particular value belongs to a vector, please make sure that you include the direction together in your data collection, because it will make it easier for you when you are doing your substitution not to forget the signs. All right, very much important. An object in free fall accelerates at 9.8 meters per second squared. We've already spoken about that downwards while the object is moving up, or whether the object is moving down. The acceleration is 9.8 meters per second squared downwards all the time. All right. Now, let us quickly look at what else that you need to expect under vertical projectile motion. Obviously, according to our exam guideline, we need to be able to sketch position versus time graph, velocity versus time graph, as well as acceleration versus time graphs. Now, these graphs, you need to be able to draw them, and you also need to be able to interpret them, because the examiner can ask you to do either or. So the examiner can ask you to draw the graph, or the examiner can give you the graph and ask you to interpret the graph and answer question based on that graph. Now, which scenarios are you going to look at, or which scenarios are examinable that you need to go practice? Where the object is in free fall, that's what you're going to look at. The object being dropped, okay? Dropped, that is when the object is in free fall. An object thrown vertically upwards, right? An object thrown vertically downwards, as well as bouncing objects. But remember, according to your syllabus, these are restricted only to balls. Very much important as you go through practicing, try to practice all these 4 scenarios, all right? Very much important. Now, I quickly gave you an example of one of the scenarios so that we can go through it together, so that when you practice on your own, you're able to see. So I'm just going to explain only one of them, right? So over here, you can see that I've chosen my direction. I said, let upwards be positive. If upwards is positive, that means that everything that goes downwards is going to be negative. So what is going on here in my scenario? I have an object being projected vertically upwards. It reaches its maximum height. It comes back to the original position, or it comes back to the thrower's hand. So how do you interpret the following scenario, looking at all the variables that you know under vertical projectile motion? So normally I'm going to label this one A, and then label this one B, and label this one C, just to help you as you are going through the explanation. Remember, we said upwards is positive. So if, for example, the initial velocity at which the ball was projected with was 5 meters per second, okay, this is the initial velocity. Because it's going up, this is going to be positive 5 meters per second. What is happening to the velocity as the object is going up? The velocity starts to decrease until it reaches a maximum height where velocity becomes 0. Then the object comes to a stop, and then it comes back downwards. As it comes back downward, what happens to the velocity? The velocity starts to increase again until it reaches its maximum where it was initially projected, where over here it will be the same in magnitude. The velocity will be the same in magnitude, but different in what? In direction. Why will point C be -5? Because remember, we have chosen upwards as what? As positive. Anything that goes up is positive. Anything that comes down will be negative. So remember, final velocity, or the velocity at the highest point, is always going to be 0. Then what do I know about acceleration? I know that acceleration between point A and point B, where the object is going up, where is the acceleration of the object? The acceleration is also going downwards, not upwards. Remember, acceleration due to gravity, which is our 9.8 meters per second squared. Since we have chosen upwards as positive, our 9.8 is going to be negative. Now let's look at from point B to C. What is going to happen to acceleration? It will remain the same because it goes to the same direction, which is that negative 9.8 meters per second squared. All right. Now, if you were to include displacement over here, our displacement here would be positive. All right. Our displacement between A and B will be positive as I'm going upwards, or as the object rather is going upwards, the displacement will be positive, and then as the object is coming downwards, the displacement will be negative. Now, let's take what we have just interpreted and go to the velocity versus time graph. What is important here is for you to know the shape of the graph. If you know that when we speak about vertical projectile motion, and then we speak about velocity versus time graph, I know very well that my graph will be a straight line. It's going to be a straight line going downwards or a straight line going upwards, depending on the direction that you have chosen. Very much important. Now let's try to put in velocity. Remember, velocity, that means the graph will only speak about the velocity of the object. Now, from here, this is the time at which the velocity of the object was what? Was thrown. It was thrown at a what? At an initial velocity of a positive 5. You still remember? This is my positive 5 meters per second. And then this is the velocity decreases constantly in the positive and upward direction. The velocity will start to decrease until it reaches 0. What is 0? 0 is this point. There is that point. Over here, this is the 0. The ball is at rest for a moment at a maximum height. All right, this is where the ball stops and then comes back downwards. This is when the velocity starts to increase at a constant negative downwards direction. That's why over here, I will have -5 meters per second. I hope you understand. It started at 5. It ended at 5. What will be the difference? The difference will be the direction. Very much important to remember that. Let's quickly move on to the next one. This will be the position versus time graph. It's very easy, position versus time graph, because it just tells you the position of the object. The object started here, it went up, reached a maximum height, and then came back downwards. All right, this is your position versus time graph. That's all you need to know, that this is when it's going up and that is going downwards. And also what happens to the gradient. The gradient will decrease as the velocity decreases, and the gradient will increase as the velocity increases. All right, that is how the the position versus time graph is going to look like. Let's quickly look at the acceleration versus time graph for the same scenario. Remember, our acceleration is constant. What is it? Negative 9.8 meters per second squared. Hence, I have it on the negative. This is negative 9.8 meters per second squared. And as you can see, it is a constant straight line. Why? Because acceleration does not change. It remains constant. Whether the object is going up, whether the object is going down, the acceleration due to gravity remains constant. Very much important to remember all of that. In this one, you can see that it's still the same scenario, but there is something different. The object has been thrown vertically upward, reaches the maximum height, comes back to the original position, passes the original starting point, and goes straight to the ground. That is how the position of the object is. Now, when you draw the graph, you'll see that this is where it was supposed to have passed, because this is where it had originally started. It started there at -5. This is +5. Now it passes +5 and goes straight to the ground to get the final velocity. Very much important to interpret what is happening on the graphs when you are doing these calculations. Let's quickly interpret this one. We are given the position versus time graph. Let's see what is it that you can see. You can see here at 0 time, this is the initial position of the object. The object was at a height of 2 meters. Before it was what? It was dropped vertically downwards. And then it took how many seconds? 0.64 seconds to reach the ground. And then the difference between 0.64 and 0.67, it is the time the ball has been in contact with the ground. Then after that, the final velocity here, after the bounce, we have the initial velocity again that allows the ball to go vertically upwards. It bounces, okay, to go to the second height, and then the second height is that 1.85, and then over here it goes back downwards to the ground after that 1.90 seconds. The difference between 1.90 and 1.97, which is 0.07, it is the time taken for the ball to be in contact with the ground after the second bounce. So this is the second bounce, and then it reaches the third height, which is the final height, which is that 1.2 meters before it goes to the ground again. So very much important to remember that this is just the position of how the object was going. Remember, at the highest point over here, VF is equals to 0, VF is equals to 0, or VI is equals to 0. Velocity is 0, velocity is 0 at the highest point. If you know how to interpret that, then we are good to go. Very much important. Right, now let us quickly take an air break, and when we come back, we are going to continue with momentum and the rest of the other questions. Right, welcome back, learners. Now let's quickly jump on to question 4, which is normally momentum. This is supposed to be one of the easiest topics that we have in physical sciences. However, we are struggling because of direction. However, we are not there yet. Let us quickly look at the definitions that you need to know according to our exam guideline. Remember, momentum, you need to know how to define momentum. We know that momentum is the product of the object's mass and its velocity. And again, this formula, you don't have to memorize it. It's there on your data sheet. You can just go there, then it will remind you that it is the product of the object's mass and its velocity. So can you see that the data sheet also provides you with not just the formulas, but also reminds you with definitions. The other definition that I want you to look at is Newton's second law in terms of momentum, which is F net is equals to change in P over change in time. Remember that Newton's second law in terms of momentum states that the net force acting on the object is equals to the rate of change in momentum of an object in the direction of the net force. So very much important to look at the formula itself. It reminds you of the definition. Also, we're going to talk about the applications of seat belts, airbags, as well as the crumple zones, to say what is the relationship between the impulse momentum theorem with the application in terms of seat belts, airbags, as well as crumple zones. All right, we'll look at that shortly. And then impulse momentum theorem. When the examiner says to you, use the impulse momentum theorem to calculate, you need to know which formula to use. So remember, the impulse momentum theorem is F net delta T equals to change in momentum. Remember, impulse is F net delta T, which is the SI units will be newtons second. Remember, it's not newtons per second. Do not put any -1 there, because you can see that the variables are multiplying each other. They are not dividing each other. Now, this F net delta T is the symbol for impulse, and impulse is equals to the change in what? In momentum. And remember, change in momentum over here, we know that it is equals to the final velocity of the object, the momentum, the final momentum of the object minus the initial momentum of the object. Very much important to remember that there is a relationship between impulse and what? And change in momentum. And sometimes when they say to you, calculate impulse, you can just calculate the change in momentum. However, do not forget that at the end, you must include that, you must indicate that the impulse would be equals to so and so, and then put the correct SI units for impulse. Do not leave the SI units as kg meters per second for momentum or change in momentum. Very much important to remember that. All right. Conservation of linear momentum. This one is easy. Most of us, we are able to define this one, which is the total linear momentum of an isolated system should remain constant. It's very much important to know which formula is associated with that one. We'll look at the different ways in which the formula can be expressed. However, for now, what we need to know or need to remember is that the sum of the momentum before the collision is equals to the sum of the momentum after the collision. That is basically what the conservation of linear momentum is saying. Right. Now, another thing that we need to be able to define is isolated system. Remember, isolated system actually just means that the net external forces are equals to 0. The net external forces is 0, are equals to 0. All right. Equals to 0. That's what you just need to know. Right. Then the other definition that you need to know is elastic collision. Remember, under elastic collision, the total momentum before and after collision is conserved, and the total kinetic energy before and after collision is also conserved. So basically, we are saying the sum of the momentum before the collision is still equals to the sum of the momentum after the collision. Also, the sum of EK, okay, kinetic energy before collision is equals to the sum of EK after the collision. However, please make sure that when you do your calculations, when you prove if the collision is elastic or inelastic, remember you need to calculate your kinetic energy separately. Calculate the sum of kinetic energy before the collision separately, and calculate the sum of the kinetic energy after the collision separately. Then compare your answers. If your answers are the same, that's when we say that the collision is elastic. Then in an inelastic collision, we're still saying that the total momentum before and after collision is conserved. However, the kinetic energy before and after the collision is not conserved. So very much important to say that under inelastic collision, the sum of EK before the collision, okay, is not equals to the sum of EK after the collision. How would you have known that? Again, you are going to calculate the sum of EK before collision separately and sum of EK after collision separately. Then compare your answers. If your answers are not the same, that is when you know that the collision is inelastic. Very much to remember that. Now, which formulas must you familiarize yourself with as you're going to be practicing momentum? All right, you can see over here we have P is equals to mv. Still under forces, you're going to see P is equals to mv over P equals to mv. You see the sum of the product of the object's mass and its velocity. You remember that mass is measured in kg and then velocity is measured in meters per second, and together they give you the SI units for momentum. Now over here, F net delta T is equals to change in momentum. This is the impulse momentum theorem. Okay, momentum theorem. Remember that theorem. That's very important to remember, right? And then over here we have the change in momentum that you also need to know how to calculate. And then basically these are all the formulas that you're going to be using together with the kinetic energy formula. I forgot to include it here. So EK formula is equals to half mv squared. It's also given in the data sheet, right? But remember, it's not given as the sum of EK, right? Very much important also to remember all of that. Now let's quickly look at come back here to say, what are the applications of seat belts, airbags, and crumble zones? Why are they important in terms of the impulse momentum theorem? Remember, the seat belts are there to do what? To reduce the force of impact, okay, by increasing the time of impact, right? And then while change in momentum remains what? Remains constant. So they will ask you, what is the use of seat belts, or what is the use of the airbags, or what is the use of crumble zones? So you must know that they are there to increase the time of impact during a collision, and then by doing that, the force or the F net decreases while the change in momentum remains what they say, right? Now let's quickly move on to the problem solving strategy that you need to consider as you are doing your calculations. First of all, you need to carefully read the problem to identify what is given and what needs to be found. As you do that, please, you've chosen your direction, then you collect your data together with the sign, right? So that when you do your substitution, it becomes very easy. Next thing is that sketch the diagram to visualize the motion, especially if you are given a question where there isn't any diagram. So make sure that you can draw, but remember there are no marks for drawing. Okay, very much important. You can just draw using blocks just to understand the scenario and visualize the motion. We've already said that it's important to choose the direction. That's actually the first thing that you're supposed to do. We need to move it over here before we can start doing anything else. Then the next thing is copy the correct formula from the data sheet. Cannot stress it enough to copy the formula as it appears from the data sheet, then manipulate it after. Then substitute with the correct direction. We've already spoken about that one. Now, when I practice momentum, normally I practice it in different scenarios. I look at 3 types of scenarios, okay? Firstly, I look at initially the objects are moving with their own velocities, and after the collision, they go their separate ways. Like I have object P and Q moving their own velocities. They collide. After the collision, they all go their separate ways. How do I write the formula? That is how you write the formula. This will be the momentum for P, momentum for Q before the collision or initial, and then momentum for P and momentum for Q final. So as I've seen here, I'm given before collision, after the collision. In this scenario, they've already given you the drawing. So all you need to do is substitute. So that is the formula that I'm going to use, which is the conservation of linear momentum. Now, what is it? I have the mass over here. I don't know what the mass is. Say I'm given the mass of P, whatever. But in this case, let's say I don't know what it is. I just continue with my substitution. I know that the mass of P is whatever. And then I have here the initial velocity of P that's going to the right-hand side. So I'm going to choose a right-hand side as what? as positive. So that means this will be my positive 10, and this one will be my negative 15, this one will be my negative 5. So that when I go substitute, I remember the signs. So that will be P will be positive 10 plus into M, and then B will be negative 15, right? And then equals to, these are all initial, equals to the mass of that, of P is gonna be negative 5 plus M into the Q, okay? That is what you are looking for. And then the rest is the relationship between you and your calculator. The most important part is this part under momentum, is if you can substitute with the correct what direction and correct formula used. Now the next scenario is when the objects were initially moving with their own velocities. After the collision, they move together and combine and stick together and move together as a unit. So which formula am I going to use? I'm going to represent momentum of object A, momentum of object B. Initially they were separated. After the collision, you can see that they are moving together, meaning that you will join their masses. Their masses will join together and they will share their final velocity. Right over here, I have the mass of object A, which is 7,2 multiplied by the initial velocity. I'm very consistent with my direction. I choose a right as what? As positive. I know that the 0,4 will be positive. Then this one, my B is stationary. Assuming that is stationary, it's 0 meters per second. And then I'm looking for the final velocity. So over here, the initial velocity will be positive 0,4. Plus into the 5,3 and then multiplied by 0. This is the initial. Everything equals to, when I come over here, I need to add their masses together. What is the mass of A? It's 7,2 plus the mass of B, which is 5,3, and they all share their final velocity. Guys, again, if you can reach the stage with the correct signs, right? Everything will be now the relationship between you and the calculator. The final answer should be easy to get after this one, which is not where I'm going to get. All right. Then last one is scenario number 3, where they are initially combined, or at the beginning of the collision, they have sticked together, and then after the collision, they are separating. Over here, I have a toy car with the toy rocket together. You can see that they are moving at an initial velocity of 2,5 seconds, right? 2,5 meters per second rather. This is their initial velocity when they are combined. After the collision, you can see that each object has its own what? Velocity. Again, I don't forget to choose direction. I take right hand side as positive. Can you see how I'm consistent with my direction? So as you practice, do not change direction and say, today I'm taking right as positive, tomorrow I'm taking right as negative. It's just going to confuse you. Just be consistent even when you are doing your calculations and practicing with that one direction. You will see how easy it is to navigate through everything. So all you have to do here, if we are assuming that this one was 5 kg and this one was 10 kg, all you need to do is add their masses at the beginning, because they share the initial velocity rather. So they share the initial, that is supposed to be initial velocity. Their masses is the 5 kg plus the 10 kg. They have an initial velocity of positive 2,5. Why positive? Because they are going to the right hand side. Then equals to, I separate them. Then I have the mass of 5 kg multiplied by 30, positive 30, and then plus the mass of 10 kg multiplied by the 0,6. So as I said, again, guys, if we can all get to here, then the rest is just the calculator. All right. I hope you guys are still together with me and we are flowing. That takes us to the end of momentum. We are quickly going to move on to the next chapter. I know most of you don't like this one, question 5, which is work, energy, and power. Most of you don't like it. But what I'm going to say to you for the sake of today's lesson is just to know the basics. The basics are the fundamental important thing for you to be able to get through this chapter. What is it that you need to remember? You need to remember how to define work according to the exam guideline. And remember, the formula for that is W is equals to F delta X cos theta. Remember, where F is the force that is doing the work, delta X is the displacement of the object, The cos theta is the angle between the force that is doing the work and the displacement of the object. Very much important. Another thing that you need to look at as you are doing your practicing the principle of conservation of mechanical energy. Remember the principle of conservation of mechanical energy. You need to be able to define it. Remember, it's the total mechanical energy of an isolated system does what? Remains constant. Once you are able to do that, then remember that how to calculate it. You say that the sum of EP plus EK, right, equals to the sum of EP plus EK after the collision. All right, that is your mechanical energy. You need to know how to use that one. The next one is the work energy theorem. The examiner can say to you, state the work energy theorem or use the work energy theorem to calculate. So when they say state, you go to the data sheet. Work net is equals to change in EK. State the work energy theorem. The net work done on the object is equals to the change in kinetic energy of the object. So from the data sheet, from the formula, I'm able to give the definition. And then when they say use the work energy theorem to calculate, the examiner only wants you to use this formula and nothing else. All right, very much important to remember that. The next one is the conservative force. Remember, the examiner can ask you to define what is a conservative force, or you might be asked to identify one, right? Remember, a conservative force is the force of which the work done in moving the object is independent of the path taken, and the only one that we are looking at is Fg at this point. You do have others such as electrostatic force, all right, as other examples of what? Of conservative forces. But at this point, the conservative force that we are looking at is the force of gravity. Very much important. The examiner can say to you, calculate the work done by the conservative force. That means that you are calculating the work done by Fg. So it's just the language issue that you need to get used to. The next thing that you need to know is to define the non-conservative force. It is the same definition with the conservative force. The only difference is that you are going to substitute the word independent with dependent. So meaning that the definition will still be a force of which the work done in moving the object between 2 points depends on the path taken. When it's conservative, it's independent of the path taken. So if it depends on the path taken, we are looking at force applied, we are looking at friction force, whether it's Fk or Fs, it doesn't matter as long as it's friction. There are others such as tension also that could be what? A non-conservative force. What is it that you need to remember? The formula associated with non-conservative force is equals to the change in EK plus the change in potential energy. Remember, EK is kinetic energy and EP is what? Is potential energy. So as long as you know definition, you know which formula to use. The next one is to define power. We know that we define power is the rate at which work is done, and there are so many formulas. I'm not even going to write them down that are associated with what? With power that you need to know. Now, under work energy and power, what is it that I need to take note of? I still need to know how to draw a force diagram and a free body diagram. I've shown you already when we were doing question 2 how to do that one. You need to be able to calculate the net work done on the object. Now, there are 2 methods that you can use to do that, but I will explain them when we get to that after the slide. That is what I will try to show you. You also need to be able to distinguish between a positive net work done and a negative net work done on a system. Remember, because work is energy, it is a scalar quantity, it's not a vector quantity, therefore it does not have direction. So what does the positive work done mean? What does the negative work done mean? It simply means that positive work done energy is added into the system, negative work done energy has been removed out of the system. You also need to state the work energy theorem. I've already spoken about that one. Solve conservation of energy problems using the equation. We have spoken about that. Non-conservative non-conjugative forces here, we have the force applied. We also have friction force, okay? Friction. That is what you need to know, that under work done by non-conjugative force, you are going to substitute work done by either friction force or work done by the force applied, or the work done by both of them, depending on the scenario. Use the relationship above to show that in the absence of a non-conjugative force, mechanical energy is conserved. So if there is no conjugative force, the non-conjugative force is 0. This equation takes you straight to the conservation of mechanical energy. Calculate the power involved when work is done. The following formulas for power. P average is equals to F multiplied by V average. Please do not forget that when you copy the formula as it appears on the data sheet, copy the subscripts as well, because the subscripts are part of the formula. If you leave out the subscripts, you are going to lose your marks. Right. Calculate the power output for a pump lifting a mass, e.g. lifting water through a height at a constant speed. So all of this are guides, are tips according to the exam guideline to help you to look at when you are doing your calculations. Now let's look at the formulas that are involved. On your data sheet, you'll see a place where it's written work, energy, and power. So this one is simple. It takes you there. So these are the formulas for work, EK, the formula for potential energy. That is, remember this one over here, or should we say this one, because we are doing English, not Afrikaans. So this one over here, remember that it is your work energy theorem, work energy theorem. And then over here, that is when you are calculating the change in kinetic energy. This is the formula for work done by non-conjugative force. Remember, two non-conjugative forces that we spoke about. It can either be force applied, friction, or tension, depending on the scenario, or all of them if they are all there. We spoke about this one. This is also another formula for power, where W represents the work and the time. Right. Very much important to make sure that you practice using all those formulas. Remember, we spoke about positive work. We said that is the work done on an object by a force when the angle between the force and the displacement is less than 90 degrees. So basically, when the force that is doing the work and the displacement, okay, are in the same direction, okay, so your cos will be 0 degrees. Cos will be 0 degrees. Very much important. 0 degrees, cos 0 degrees will give you positive 1, which will give you positive work done. Negative work done on the object, it is when the force, let me write it here, the force and the displacement are in opposite direction. Okay, that will give you an angle that is between 90 and 180 degrees. But in this case, we'll use cos 180 degrees, which will give you -1, and then it will give you the negative work. All right, very much important. Zero work is done when the force and the displacement are at 90 degrees. So if the force and the displacement, like normal force, for example, and the displacement of the object 3 meters to the right hand side, that means normal force is not doing the work, because the normal force and the displacement of the object are perpendicular to each other, or they are at 90 degrees. Why? Cos 90 degrees in your calculator will give you 0, and any number multiplied by 0 will give you 0 work done. All right. Hope we are together there. Remember, I said to you, I'm gonna show you the 2 methods that you can use to determine the net work done. The first one is that you first draw the free body diagram or force diagram of all the forces that are acting on the object. You know, I like to do this one. You never go wrong when you draw all the forces that are acting on the object. Then from there, you determine the angle between the force of each force and the direction of the displacement. You check, does this force how is the relationship between the force and the displacement? Is it in the same direction? Is it in the opposite direction? Or is it perpendicular to each other? If they're in the same direction, work is done. If they're in opposite direction, work is done. If they're perpendicular to each other, then work is not done. Right? Then you use the formula W is equals to F delta X cos theta to determine the work that is done by each. And then you can use it and say, since I have work done by Fk and work done by the force applied, then you can use work net is equals to the work done by that Fk and the work done by the force applied. All right, that is one way you can do the calculation. The other way you can do it is that you still draw the free body diagram. Then you do what? You ignore all the forces that are not doing the work. You only focus, or you draw the free body diagram with only the forces that are doing the work. Again, how will you know that they're doing the work? If the force and the displacement are in the same direction or opposite direction. That's when you know that work is done. Then what you can do, first you calculate their F net. How do you calculate their F net? You calculate F net by saying, okay, what is the amount of force 1? What is the amount of the force 2? If there's 3 forces, what is the amount of force 3? Then from there, you calculate the work done on the object using this formula. So you are going to take that F net that you calculate over there, then you substitute it here. All right. And then that is how you're going to calculate your net work done on the object. Now let's quickly look at a scenario. I'm just going to give you 2 minutes to try to do this on your own using the 2 methods that we just did, and let's see if you can get it right. Now let us try to do this one together. It says, calculate the net work done on a box lying on a horizontal surface by 100 Newton force and a 20 frictional force, which acts at an angle of 20 degrees to the horizontal. The force displaces the box 3 meters as shown in the diagram below. So from the diagram, step number 1, we're going to start with method 1. Okay, method 1. This one, we use work net equals to work done by 1 plus work done by the second one, by the second force, right, that is doing the work. So the first thing that we are going to do, we are going to draw a free body diagram that shows all the forces that are acting on the object. Now, here's my free body diagram. Remember the God-given force, Fg. The force that is force A at an angle of 20 degrees. And then we have the normal force, which is perpendicular to the surface. Then we have what we call the Fk, which is the kinetic friction force. Then the next thing, what you are going to do is that you are going to break down F into components because you are doing the calculations. Remember, you only break down F into components or when you are doing the calculations. So my F is acting at an angle. So if I break it down, it will give me 2 components over here. So I'm breaking down this one to here. It will give me Fy as well as Fx. Now my Fy is F sine theta, and then my Fx is F cos theta. All right. So over here, the next thing I'm going to do is to identify the forces that are doing the work. Okay. Remember, only the forces that the force and the displacement must be in the same direction, or the force and the displacement must be in opposite direction. So let's look. Where is the displacement of the object? Is 3 meters to the right. Right. 3 meters to the right hand side. Right. Let's look at Fx, which is the component of F. It's going to the right hand side, so it's doing the work. F cos theta is doing the work because the force and the displacement are in the same direction. What about the normal force? The normal force and the displacement is 3 meters to the right. They are at perpendicular to each other, which means that the normal force is not doing the work. What about Fg? Fg is also not doing the work because Fg and the displacement are perpendicular to each other. What about Fk? Fk is in the opposite direction of the 3 meters. The 3 meters is going to the right, Fk is going to the left hand side, so Fk is doing the work. All right, so the next thing we are going to do, we are going to calculate the work done by the forces that are doing the work separately, right? So the first thing that I'm going to do is calculate the work done by Fk. The work done by Fk is going to be Fk delta x cos theta. What is the value of my Fk? I'm given here 20 newtons. That will be 20. What is the displacement of the box? Is 3. So it will be multiplied by 3. What will be the angle between the force and the displacement? They're in opposite direction. So cos will be 180 degrees. So this will give you negative 60 joules. This will give us negative work. Negative work is done. That means that energy is leaving the system. The next thing that we are going to do is calculate the work done by the component of F, which is the work done by Fx, is equals to F cos theta multiplied by delta x multiplied by cos theta again. What is the value of the force? Is 100 newtons. So 100 multiplied by the cos of what is the angle is 20 degrees multiplied by 3, which is the displacement, and multiplied by the cos of 0 degrees. Why cos 0? Because Fx and the displacement are in the same direction. So when you punch into the calculator, I get 281.90 joules. So what does this mean? This is positive work that is done. From here, I then go to work net is equals to work done by Fk plus work done by Fx, which is negative 60 plus 281.90. If I calculate it correctly, I get 221.939 joules. 9 joules. That is how much I get as the net work done. This is method 1. All right. So quickly we are going to go to method 2. Method 2, we've already drawn the free body diagram. We are going to draw the free body diagram of only the forces that are doing the work, which is Fx as well as Fk. Now we are going to calculate Fnet. Fnet is equals to taking right as positive, because remember the force is a vector, it must have magnitude and direction. I take Fx is positive plus into negative Fk. Right, now let me do the substitution. How much is my Fx? It is my 100 cos of 20 degrees minus Fk. How much is Fk? 20 degrees. Then when I do my calculations very well, I think I got something like 73.97 newtons. This is my Fnet. The moment I'm done calculating Fnet, I go to the formula. Work net is equals to Fnet delta x cos theta. Then I can substitute. So my work net will be equals to, what is my Fnet? 73.97 multiplied by 3 multiplied by the cos of 0 degrees. Why is it cos 0 degrees? Because the Fnet is positive, is going in the direction of the motion. So hence the Fnet and the displacement are in the same direction. Hence it's cos 0. And then when you punch into the calculator, it should give you the same answer, which is 221.91 joules. Okay, so as you can see, we get the same answer. So these are the two methods that you can use to remember, and you can choose any to do your calculations. Guys, we are done with work, energy, and power. Let's quickly jump on to Doppler effect now. This is the most easiest chapter, but if not done correctly, you can miss a lot of marks. Now, what is it that you must look forward to? You are looking forward to having one definition to remember under Doppler effect, which states that the change in frequency detected by the listener, because the sound source and the listener have different velocities in relation to the sound propagation. Okay, please make sure that you go and look at that definition very well, check it, and make sure that it's according to the exam guideline. Another thing that you must remember, what is the application of Doppler effect? We know that we use the Doppler flow meter to measure the heartbeat, or the Doppler flow meter is used to measure the speed of the blood flow, and then the sonar or the radar, it is used to measure the heartbeat of a fetus. So very much important. The examiner can say what are the instruments that can be used in Doppler. Instruments is Doppler flow meter and sonar or radar. When they say what are the uses, you can say that they are used to do what? To measure the blood flow and also to measure the heartbeat of a fetus. And then the next thing that you must remember is to look at redshift. Remember, we no longer do blue shift. You must look at the redshift. Remember, redshift is when the spectral line are shifted towards the red, where they are longer wavelength, and then we have shorter frequency, which is an indication that the star is moving away. It's normally used by astronomers. So go check and look at the definition of what redshift is. Okay, so quickly let's look at when we are talking about Doppler effect, just to give you a few things to take note of or to remember. Remember here, what is important is the relationship between the frequency and wavelength. We are using the formula V is equals to F times lambda. You remember this formula in grade 10 and also in grade 11. So what is the relationship? We know that the relationship between wavelength and frequency is inversely proportional. Once you increase the wavelength, the frequency is going to decrease, as well as the pitch is going to decrease. Over here, I've given you the diagram to make you remember the wave fronts. Remember, at lower frequencies, the pitch becomes lower, which means you can see that the observer and the source is moving away from the observer. So as the source is moving away from the observer, that means that the wavelength is increasing and the frequency decreases because the pitch of the sound decreases, which means that you are going to hear the sound of the ambulance a little bit lower. So the sound is going to keep on decreasing. And then at higher frequencies, you know that as the observer, that means that the ambulance is now approaching you or coming towards you. What happens? The wavelength decreases and the frequency increases and the pitch also increases. Hence, you're going to hear a louder sound when the source is approaching you rather than when the source is moving away from you. Very much important to take note that when the source and the listener they are both stationary, there is no Doppler effect, because that means that there is no change in frequency and there is no change in velocity. If there is no change in velocity and there's no change in frequency, then therefore there's no Doppler effect, which indicates that the frequency of the listener will be equal to the frequency of the source. Very much important to take note of that. But when the listener is moving towards the source, we've already said that the wavelength decreases, okay, and then the frequency does what? Increases. And then when the listener is moving away from the source, we know that the wavelength increases and the frequency decreases as the speed remains what? The same. Very much important to remember that. Now, these are the formulas that you need to look forward to. They are under waves, sound, and light on your data sheet. We have this formula that I was talking to right now, which is a very nice formula to play around with. We also have this formula of the period and the frequency, which is also from grade 10. Very much important to look into that. Now, the most important formula is the Doppler effect formula. Remember, you copy the formula as it appears on the datasheet with both the signs. When do you start choosing the signs? When you are doing your substitution. Remember, when the source is moving towards you, the signs on top, the sign will be positive, and then the sign below it will be negative. You can never have the signs that are the same. You can't have positive and positive or negative and negative. Always remember that the signs will not be the same. This is when it's moving towards you, okay? When it's moving away from you, then that means the sign on top will be negative and the sign below it will be positive. Very much important to look at that formula. All right, very much important to go and practice, and practice makes perfect. Quickly, let us look at this activity together. Now I'm going to give you your own time. Let's say 2 minutes again. I think it's a very simple activity. You can really do it in 2 minutes. Let's take 2 minutes of your time. Try to do this one based on what we just spoke about, and let's see if you can do it.